Hey, today part two is we're going to look at an exponential with an irrational base. Talk about irrational numbers quite a bit. Remember, an irrational number is any number that goes on forever as a decimal with no repeating behavior and no end. So, be like square root of 2, square root of 3, square root of 7, etc. Any non-perfect square root is irrational, and pi. And remember, we use a symbol for pi because it has infinite many decimals. But remember, pi is found by a unique relationship. It's the circumference or the distance around a circle, right? If you cut the circle and you laid that piece of string out flat and you measured it, that would be the perimeter. And if we divide that by its diameter, every circle is going to get you pi, no matter how small or how big it is. And so that's where pi came from, is people started dividing the circumference of a circle and divided it by its diameter, and they kept getting this irrational number that was the same no matter how big or small the circle is. So in the same kind of way, we're going to run into another irrational number that you may or may not have um, looked at yet. So the first thing that we're going to do is we're going to take this and we are going to plug it into our calculator. So this is where the irrational number comes from. So I have 1 plus 1 over x. So here's that. This is our rational piece, right? And we're going to raise it, whatever that denominator value is, we're going to raise it to the same power above. So let's do that. Huh, computer froze. Oh, maybe not. There we go. Perfect. Okay, so what I'm going to do is, like I said before, the input variable is going to be x. So whatever I input, it's going to go in the denominator of this fraction, making it small, 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 right? The bigger this x is going to get, the smaller this fraction is going to become, and it's going to then add to 1, and then we're going to raise that to a power, okay? So like 1 over 100 is a small number, and then we're going to add that to 1, and then we're going to take that quantity and we're going to raise it to that 100. And then what you find out is this becomes a horizontal asymptote. So I plugged this already into our calculator, and here is the equation. And then I'm going to go to the table, and we're going to look what happens. Now notice I can't use 0 because remember I'm plugging that into a denominator of 1 over x. So when I plug in 1 over 0, right, we already know that's undefined. But what happens as my numbers get really, really big? Well, it would make sense that since my fraction is getting smaller and smaller and smaller, and I'm adding it just to the value of 1 and then raising it to a power, this is going to be approaching a value. So, and if we keep going down and increasing this value, then you will see that it's starting to approach a single number or an asymptote. It's never going to become this number. It's irrational, so it goes on forever. But it's going to try to approach it, approach it, approach it. And so what we call this number is E. And if we take a look at the graph of this, it's not a really good picture. You'll notice that it ends up being this asymptote right here in the middle between these two graphs, this y equals 2 point. Both sides are approaching that asymptote as whether it gets negative or if it gets positive. Okay, and we're going to give this an E, and this is 2.7. What did we say? Let's take a look. I almost forgot. You have a button in here. Second, and then the natural log. We're going to talk about that. If we just raise it to the 1 power, it's 2.718 approximately. Okay, and what we're going to do is we're going to graph these. These are applicable to a lot of real world applications. A lot of financial models will use this base E in an exponential. So right now we're just going to introduce it as an exponential function. Obviously, this is going to be a growth because my base is greater than 1 because it's about 2.718. And we're going to input some values. So let's do again -2, -1, 0, 1, 2, 3. And then we're going to write e to the -2. Typically, we do not want to estimate this value right off the bat, so we would write 1 over e squared, and this would be 1 over e, and anything raised to the 0 is 1, e to the 1, e squared, and then e cubed. Now, for my graphing purposes, and still going to have this asymptote at y equals 0. I'm definitely going to want to get some estimate value. So I always kind of think, hey, this is about 2.5. So you think, in that way, if you didn't have a calculator. But we're going to investigate this a little bit more. We're going to go to my graphing calculator, go to y, figure out what we had here. We're just put in e to the x. And we'll go to, probably messed up my table. So we'll start off at the table and we'll look at full values. We start off at -2. So you get something imperfect like 0.1. Can't be much accurate than that. And then -1 is about 0.4. And then e to the 1, well, we know that's about 2.7. And then we know e squared is going to be 7.4. And then e cubed was 20.1, which we won't have. Okay, and then I'm just going to graph this. So -2, 1, 0.4, 0, 1, and then 1 and 2.7, and then 2, 7.4. We'll notice it is a growth approaching that asymptote. Okay, and if you can kind of notice, here's a compound interest equation, which you've probably worked with. And if you can see, this is really where it started to come from, this E. You can see right here. Here is my input, right? Here's that 1 over x part, even though it's r, but they just did an algebraic trick to get rid of that, and x. So when you compound continuously, this is where you end up with e. And we'll talk about that more tomorrow when we go over these interest formulas. And then we have the continuous compounding interest, and then notice that's where the e comes from. And we'll talk about more of those tomorrow. I just wanted to put them on there today so we could connect to e a little bit. Maybe it's a little fuzzy right now, but we will make links to the compound interest and the continuous compound with e. The next thing that we want to look at is we want to look at the transformation of these exponential functions, and then we'll be done today. So the first thing that we're going to look at is the graph of 3 to the x. So I know that's a growth. Now I'm just going to, because I'm doing transformations, I'm going to get those 3 parent functions. So 3 to the -1 is a third, 0, 1, and then 1, 1, 2, 3. Goes by 3 points. Okay. Now this one, remember, is my transformation. So what am I going to do? This -3 up at the power, that's my right 3. Remember, it goes the opposite way. So now I'm going to move 1, 2, 3, each one of these. 1, 2, 3 to the right, 3. And here is my transform function. This one's 3 to the x minus 3. And this one was 3 to the x. The last one, this one is going to be down 4. And so I'm going to shift all my points down 4. 1, 2, 3, 4. But the key is you also have to make sure you transform your asymptote down 4 also, which is at 0, so be at -4. So this one will be down 1, 2, 3, 4. And this one, 1, 2, 3, 4. And there's my function, 3 to 4. And that should, all of this should be mainly a refresher. Even these formulas you should have used probably before. I'm not 100% sure. But then what E is in defining that might be a little bit different. And we'll talk more about this tomorrow. And then my last one is the graph 2 to the x. This one also we're dealing with a growth because my base is greater than 1. I'll be multiplying my bases by 2. But these are my reflections. So I'm going to start by plugging in -1. 2 to the -1 is a half. 2 to the 0 is 1. And 2 to the 1 is 2. And there is my parent function, 2 to the x. Remember, if I have a negative out in front, that is an x-axis reflection. So I'm just going to reflect across my x-axis. That does not change my asymptote. And I'm just going to be approaching it from underneath. This is -2 to the x. And my last one, this one would be a y-axis reflection. This is another way to look at, remember how we talked about growth and decay earlier and how we use the property of exponents to write that as 1/2 raised to the x. Well, you could also look at it as a reflection. And so that's what we're going to do here. And if I reflect across this axis, I'm going to start with 1 raised to the 2. So that comes over to this side. My 0, 1 is on the reflection line, so it stays. And then my -1, 1/2 becomes 1, 1/2. And there's my decay function of 2 to the -x. And so tonight you will have some book homework. We'll kind of mix it up. Some will be book homework and some will be some Delta math, and I'll just post that online as we know which one is which. And I'll see some of y'all tomorrow, and I'll see the other half on Thursday.